Hi, I will give you a short introduction how to use the A to E converters on PSoC 1. So here I've opened a PSoC designer. Let me just make a new project there. Name it, for example, TKP and ADC. There. Wait for a second. Okay. There we have the chip design first, and we just take the A to D converters, take our what we need for selecting the A to D converter. You can relate to the Cypress Semiconductors application notes. I'll just take the first one, ADC incremental A to D converter, and for clarity, I'll just check the first one with the first order modulator. So basically, they have these different configurations have basically different properties, and fundamentally for 8-bit or this exercise, what we have later on, you can use any of those. And in any case, for any application, you would be optimizing the correct kind of converter in any case. Okay, first things first, I'll rename it. Name is now ADC Inc. instead of ADC Inc. 1. And for clarity, I will just use the unsigned presentation. Practically, the unsigned representation is good for signals, unipolar signals, and since this PSoC is actually running a 0 to 5 volts, I would always use unipolar and later on do the calibration if needed. Okay, resolution. Again, for clarity, I'll take 8 bits. That fits nicely in the 1 byte. Okay, the next one, data clock. Okay, for that one, we need to take a look at the data sheet. There. So let's go to the parameters. Parameters say about the data clock. The data clock determines the sample rate, and it must be more than 250 kilohertz, and the maximum data clock rate is 8 megahertz, and that actually defines the sample rate. The sample rate has this formula. So more you have bits, longer it takes. Since it's basically we are just testing the A to D converter, I will just use the highest possible clock rate, which is 8 megahertz, and I can produce it using PC1 clock divider of their value 3, and that would actually divide the 24 megahertz system clock with 3, which is exactly 8 megahertz. And now we have the data clock ready. The next parameter is actually positive input, which is our signal input, and it has these 6 different locations you can take it. I will just take it for now. I will just click on the port 2.1. Now it's hardwired into one of the ports. Remember, port 2.1 is actually not good, since that's also where this kit has the signal for the LCD display, but we will change that later on. A negative input. Now we are using unipolar signal, so basically we just neglect that one if we have the disconnected negative input gain. It means that we are using just single-ended signal. On the exercise, you will be using this signal from a variable resistor, which is on the same board, and therefore you don't really gain anything having a the differential signals. Okay, clock phase is normal. read the data sheet if you want more information on that one. What does it do? Same for the pulse width, and then PWM output. That's the digital part of this A2D incremental, the ADC incremental converter. You can actually also have the incremental value as pulse width out of the system. So that's also digital signal. But in this case, we are not using it. I click just none. Okay, that's all you need to do for A2D converter. Now, basically, just generate configuration files, and if you want to test that it works, I recommend you running the basically the sampling code and include an LCD design into your circuit. So that should verify that you have a functional A2D converter on the board. Okay, but there was a problem. You are using LCD in port 2, and we have now the signal on port 2. How to avoid that one? Actually, if you take a closer look on the positive input, you can also connect the positive input to some of these blocks, for example, ACB00, which is this block here. But unfortunately, it doesn't have anything there yet. So for rerouting the signal, I can actually include there a PGA, which is programmable gain amplifier. Okay, which if I take the programmable gain amplifier, now my A2D converter actually have a signal on it. We just need to now change the some of the parameters. So, for example, since this is just for the rerouting the signal, I can click the gain to 1. So it's just a voltage follower. The input, now I can use analog column input multiplexer, which is right here, and immediately have access to port 0, the odd pins. If you want to use the even pins, then you must actually move this one into a different block, like that. Then take the input signal not from ACB 00, but ACB 01. Okay. And now I can actually connect the input to this 8-bit multiplexer, which basically can be used to connect to any of the port 0 pins. For example, port 0.2, that will be there. Or select from this multiplexer to get it from port 0.3. Okay, that's how it works. Quite simple to configure. Reference, I would use analog ground for voltage references. That's a good solid reference, or at least it's the same reference as our A2D converter has. And if you want the output from this programmable gain amplifier, you will you can connect this one to analog output bus. Okay, but now we are just disabling it. So fundamentally, this is all you need to reroute the signal from the pin one you want to programmable gain amplifier, and then to the incremental A2D converter. This is not quite yet everything, since in addition to these, there's the reference multiplex settings, which have 8 different settings you can select from. If you want so-called accurate measurements, then you would like to use most probably the band gap reference. So band gap reference in PSoC is actually a 1.3 volt band gap diode, and that gives you a decent voltage reference for measurement purposes. There are different settings. You can run it as band gap plus minus band gap, which means the 0 or analog ground level would be at the band gap, and then the range for the analog circuits would go operating range from 0 to 2 times the band gap. Okay. But for 5 volt operations, actually 1.6 times band gap plus minus 1.6 times band gap would give you roughly a value that is quite nicely translated into volts. Since 1.6.1.3 is almost 4096, it's actually 4080 millivolts, but close enough for this kind of small applications. There's only less than 1% difference to the real setting. So if you had a 12-bit A to D converter and divide 4080 millivolts into 2 to the power of 12, you would actually get about 1 millivolt per as a resolution for your A to D converter. So that's my favorite setting, 1.6 band gap plus minus 1.6 times the band gap. There are also other settings, but there are more information again on the datasheets. Okay, there. Now I think I have all the settings ready, so I can generate a configuration file and then just do the just add the code here. Just a reminder, when you have this, now we have two modules. It's very often that you forget to start the programmable gain amplifier. Although we are using it only for the buffering amplifier, you still need to start it, since basically calling this PGA start function with PGA, for example, high power setting. Sorry, PGA high power setting. Only after calling the function, the signal is there to your A to D converter. If you do not start the module, it doesn't do anything. The signal doesn't flow through the system, because this function PGA start or any start initializes that module. It sets the register values such that the that block functions as programmable gain amplifier with given amplification gain. Okay. Then of course you need to do some coding, but anyways, that's how simple it is to add an analog to digital converter into your PSoC 1 design. And for rerouting purposes, you would need also the PGA module there. Okay, that's it.